It's been quite a journey. I've spent about a third of my career in industry, about a third in government service, and about a third in academia, really at MIT Lincoln Laboratory. And each of those segments of my career, I've been able to work with remarkable people and some really tough problems, and learn a lot. And it's really about the team of people that you work with that I've cherished. In graduate school, I had funded work. I had work that was funded by the Office of Naval Research. Early in my career, I saw a lot of development and was part of contracted work with the Army, with the Navy, and with the Air Force Research Lab. So very early on, I got to learn some of the technical community within federal government, at least in those areas. In industry, I worked at Ford Microelectronics, I worked at IBM, Westinghouse, no longer here, part of Northrop Grumman actually. But it taught me when I went into government service that there's a remarkable team of technologists all across our government laboratories. And so when I was asked to join DARPA as a program manager, and later as an office director in two of the offices, I had the remarkable opportunity to work with a lot of those government technologists and, of course, industry and academia. And then later, as Assistant Secretary of Defense for Research and Engineering, I kind of saw the whole enterprise. So it's kind of, I've seen it from different angles. No shortage of talent and no shortage of passion and commitment to the mission. DARPA is a really unique and important place. One of the probably most unique organizations across our federal government, really is. It was formed in 1958, right after the launch of Sputnik. And the purpose of DARPA was to prevent technological surprise. You think about the impact that Sputnik had on not only the military impact, but the psyche of this nation. All of a sudden, many Americans saw a Russian satellite. Couldn't imagine it, and yet it was there. And the question was, how do we prevent that from happening again? So DARPA's mission is not only to prevent technological surprise, but to create it. You need an agency, you need an activity that can take on that risk, without lots of issues if you don't prevail. So if you think about it, DARPA's budget is $3 or $4 billion. It seems high, but compared to the DoD budget of $800 billion, it's a small fraction. So DARPA bets on high impact concepts that enormous risk, yet if they're successful, they have enormous impact. And I just found that absolutely astounding and really attracted me. So when I was asked by former DARPA director to consider coming to DARPA as a program manager, was kind of recruited, I jumped at it. I jumped at it because it's a crucible to create new ideas. You've got lots of latitude. You've got lots of support and the ability to convene remarkably talented people to attack problems that could have a big impact if you solve them. And that just challenged me. I wanted to be part of that. And not only was I part of it as a program manager, I kind of went back on two other occasions and led two of the offices there. I led the Microsystems Technology Office, and I helped stand up the Information Process Technology Office, both of which were trying to look at what's the future of microelectronics going to look like. Today it's in our conversation, but a lot of those conversational elements started back in the early 90s, mid-90s. In the mid-70s, early 80s, DARPA launched a program in very large-scale integration technology. The Air Force led the program, the VISIC program, which was looking at how could you build computer systems with microelectronic components at scale. How could you build thousands and thousands of a computer chip with thousands of transistors in it? And it sounded like a huge challenge, and it was, because it required design engineers, it required physicists, chemists, process engineers, disciplines from all over to come together on those issues. today, the chips that are in our iPhone or Android contain billions of transistors. And we don't think anything of it. It's just kind of hidden. It's there. But those core technologies were seeded by early work that was funded by the Department of Defense, largely for defense applications. And of course, that lever has shifted. That balance has shifted. Most of the applications today are commercial. I would say the first big program, the first big investment that DARPA made to really propel the semiconductor industry was probably Semitech. DARPA made roughly half the investments. It was $100 million a year for each of 5 years, coupled with an industry investment of the same amount. I was the program manager at DARPA for some period of that, and spent a lot of time with the industry partners to help them accelerate their pace. And of course, at that time, this was in the early 90s, at that time, the threat was that our technology was being overcome by developments in Japan, that Japan would take that industry. So the US Congress made the investment. DARPA was the executing body for this. And we brought industry and academia together to really make those investments. And it was, it was a magical time. In fact, during that same epoch, during that same period of time, I was leading much of the work in microelectronics. I had a colleague that was leading the advanced work in photonics, and there was another colleague that was leading all the advanced work and early work in the MEMS technology, the micro electrical mechanical systems technology. All three of those became industries of what exists today. So if you look at what's in your smartphone, what's in your Android, what's on your desk, what's in your Leica cameras, what's in, everything that we use every day, the vehicles that we drive, much of that technology was seeded by early development some decades ago. And these were long-term investments. They were, we were betting on technologies that had yet to be proven. We were trying to understand the fundamental physics of the devices. We were trying to understand the fundamental chemistries and how we would use them for defense applications. That body of work was done, and the commercial sector realized that there's something really big there that could have an impact in commercial products. And this thing just sort of spun, and people have adopted many of those technologies. You hear that in use today. There's a very famous and well-used framework that we went back to over and over again. It's called the Heilmeyer Catechism. George Heilmeyer was a DARPA director in the mid to late 70s. Remarkable guy, a colleague and a mentor. He's a fellow that I spent a lot of time with. And he had a framework that kind of was the way to think about a DARPA project. And it had 4 or 5 questions. And the last one, by the way, is what's it going to cost and how long is it going to take? Usually industry starts with that. But he inverted it. His first question, what problem are you trying to solve? Be precise, be clear about what problem you're trying to solve. The second question, I think, was how's it done today and what are the barriers? Like really understand what are the limiting issues today. Third question is what ideas do you have and have they been proven? And then you kind of get into what are the milestones that you'd want to see? Not the programmatic milestones, but the technical milestones. And then lastly, what's the cost, what's the timeline, and so forth. But the fundamental question of what problem are you trying to solve? If you really think hard about that, that's a real element of decision. And if you're willing to take some risk, if you're willing to take a lot of risk, you open the aperture to some remarkable ideas. Now, not all of those are going to see the light of day. And, you think about a portfolio that the country has in technology investments, there's certainly a need for a small part of that portfolio to be those ideas that are well thought through, think Heilmeyer Catechism, but those ideas that if you succeed, you'll fundamentally change an industry. You'll fundamentally change a capability for our national security. You'll fundamentally change the nature of something in a very deep way. And I'll tell you that the programs that I led, the programs in my office, those are the guideposts that we used. In some fashion, I mean, we kind of maneuvered here and there, but at core, it was never about the funding initially. It was always about what's the substance of the idea that you're really trying to pursue, and do you really understand it? DARPA is very risk averse. Industry is not. Industry will take a portion of its revenue and put it towards long-term development. But there's got to be a path towards revenue in industry. DARPA is really willing to take on an idea if you can show the essence of the idea, if you can describe it, and if you can describe what difference would you have if you were to achieve that, and really the underlying science of it. DARPA generally will make that investment and has done so in many areas. GPS was something that was considered today as a moonshot. It was a remarkable idea. And today it's embedded in cameras, it's embedded in our cell phones, it's embedded in our cars. We don't even think about it. And the same is true with many other technologies. But I think the core difference is the amount of risk that industry, the amount of risk that DARPA is willing to take as compared with the risk-averse nature that industry makes its investments with. I think that's a big distinction. My view is that a moonshot has to have scale, has to have complexity, and has to have impact. When we thought about the Gemini moonshots, when we thought about the NASA moonshots, there was some level of impossibility. Like, this is going to be so hard, we're not going to be able to do it. But scale was important, and impact was important. In the projects that I led, in the work that I led at DARPA, and the work that I oversaw across the department, those initiatives that seemed so hard, that were well defined, that if you could solve them, if you could really bring some solutions to bear, would have a remarkable impact. That's what I think of a moonshot. Certainly, solving world hunger could be considered a moonshot. Certainly, global warming is a moonshot. So, addressing that. But in a more sort of bounded area, in the initiatives that I led in microelectronics, we looked at technologies that, if we could really achieve this, it would have a big impact in the capabilities that we could field. As a program manager at DARPA and later leading the Microsystems Technology Office, we looked in the early 90s at how microelectronics was going to scale. We had started to see the emergence of silicon technology in a few consumer applications. You saw them in video games, you saw them in some other applications that were starting to emerge. We saw them in the early camera imagers. But the question was, how is this going to grow? And how could we encourage it? How could we scale this technology in a really big way? The Defense Department is keenly interested in all of that technology for sensors, for communication, for all sorts of applications. So we were trying to understand how do you really scale silicon from thousands of transistors to billions? How do you do that? And it was clear to us that we had to make some big investments, not only in the transistor, but in the materials, the chemistry of the transistor. And so we launched programs that use this fancy material called gallium arsenide, another material called gallium nitride. We used all these exotic materials, and we essentially built an industry to complement what was being done in silicon microelectronics in other technologies. But the benefit was that opened the door to new types of communication. It opened the door to onboard computing in a very low power way. It opened the door to GPS in your hand. It opened the door to all these applications that all of a sudden, our imaginations ran wild. Okay, now I have the elements to actually do something much bigger than just computing in this one point. Those were all they were kind of moonshots. They were, we had an idea. There was a technical community that we identified, largely academia. It was a bit exploratory. We had some enormous challenges. There were Nobel Prizes that came out of that work, several in fact. And it took an industry and DARPA leadership to convene that industry to actually launch these initiatives. And today, we put all that in place, and today you've got a microelectronics industry that's now the backbone of our economy in many, many ways. So that's one example. And those were all, every one of those was a bet on a technology that didn't exist. And getting a contractor, getting a scientist to really describe how are you going to achieve that benefit? How are you going to go 1,000x? How are you going to improve something by 1,000 or 1,000,000 times? What are the ideas that will allow you to do that? And what confidence do you have? And in some cases you understood it. In other cases, it's a bet on the person. It's a bet on his or her experience. Okay, I'm going to let you run for 6 months. We'll see what comes out of it. If you can understand a little bit more in 6 months, we'll go a little bit further. It is a team sport. Very few innovations happen with a single individual. We don't live in a Newtonian world of one person, one invention. Teams really make things happen. And it's important at the beginning of any project like this, and I've seen this across many industries, to really actually go back to the Heilmar Catechism and really think carefully, what problem are we trying to solve? What opportunity are we trying to unlock? And can we describe it? Can we build an architecture? Can we describe what it is we're trying to achieve even before we have the elements in place? And that's actually part of that's the part of the job I really enjoyed at DARPA, and the part of the job I really enjoyed in the Pentagon, working with people to try to really understand the core essence. ISI is a remarkable organization. It's very unique. The connection with USC, University of Southern California, is quite unique. My early interactions with ISI were with Cesar Pena using the MOSIS program at ISI, and with Keith Unkefer, who had, I think, established ISI, and then later with Bob Parker with some of the high-performance computing programs. But what I found really interesting, actually two things. One thing I recall vividly, my first visit to ISI on Admiralty Way in Marina del Rey. I went there as a DARPA program manager. And Cesar took me up to it was a 6th or 7th floor, to show me one of the nodes of the ARPANET. And I was astounded. In this sort of undescript building, kind of hidden in the top floor of this building, little corner of the building, was one of the nodes of the ARPANET. And Cesar was really proud of this thing. I was excited to see it. My focus was on again, the microelectronics development and the MOSIS work that ISI led, the advanced development work that allowed mere mortals to get access to semiconductor fabrication in a very low-cost way, trained thousands of students across many universities, and I found that remarkable. I mean, here you're trying to build an industry, and we just didn't have the workforce. Universities were just then starting to offer courses in semiconductor device technology and design. The factories were just now starting to come together. And foundry services, that is, the availability of those factory production runs, weren't available to more than just a few users, commercial users. And ISI found a way to put together designs from many, many design groups, integrate them, and give those design groups access to technologies that large companies only had access to. So all of a sudden you had a way for a university researcher to do his or her work using the best technology that American industry had. And I found that astounding. And today, I talk to colleagues all over the country, at universities, but also in the commercial sector. And many of them have told me about their experiences using MOSIS as their first introduction to manufacturing, because it gave them an entry into a manufacturing field that they had no access to. So at DARPA, I wanted to sort of leverage that. I wanted to use that, and we did. So we had programs with ISI to act as transitions for many of the technologies that we had developed, and those still exist today. Think of designing a chip as having a phase where you're actually drawing the chip on a computer screen. And then you submit that design to a manufacturing plant, and the manufacturing plant goes and produces it. There were many universities that could do the chip design. There were lots of places to do that. But access to the manufacturing companies was very limited. What ISI did, it came up with a way to integrate designs from multiple users onto a common design mask and submit that to a manufacturer, so that the manufacturing costs would be amortized over the number of users. Access would be available to a much broader set of researchers, developers, and you'd have access to a broader range of manufacturing partners. Sounds simple, but it was a hard thing to do, and it had a remarkable impact in training thousands of engineers in this whole technology. It really was part of this whole revolution. And MOSIS had the additional challenge of integrating disparate designs, different designs from multiple users. So you might be submitting a design, I might be submitting a design. MOSIS was there to make sure that our designs didn't compromise each other, that what I put on my chip wasn't going to compromise what you put on your chip in the manufacturing process, and kind of oversaw that. And so ISI was the integrator of multiple parties that were part of a unified design, and they were also the partner to the manufacturing arm. And that's still the case today. So it was something that was needed. No one else came forward with that idea. It was a very unique idea, and it had remarkable impact. It also had a lot of technical challenges, right? So think about it. I'm a manufacturing company, and I'm now going to accept a design from some university that's taken a bunch of research topics and put them into my fab, and you're going to tell me that you're not going to, mess up my process? I mean, there had to be some level of trust and understanding, and it was based upon the technical depth that ISI had to assure the foundries that, in fact, what they were submitting for manufacturing wasn't going to compromise the manufacturing process. So it was a level of risk, but it was supported by people that really understood the design at ISI and really understood the manufacturing process. And so, I've done work with ISI and with USC since. In fact, I'm working with ISI now. And the thing that attracted me to that, even today, is the level of technical understanding that the ISI team has. That has only grown, and I enjoy that. It's a really refreshing part of what I see there. Our nation needs a channel of creativity and innovation that's unconstrained. Maybe not a lot, but a little bit. You need a channel for thinkers that actually want to try a few things without being constrained by how much risk somebody else is willing to grade them on. And there's some responsibilities with that as well. A researcher that takes on a project that's of enormous risk has to be able to describe it. They have to be able to outline where they think the challenges are and how they think they're going to approach those challenges and what might those milestones be along the way. Those are all programmatic sort of guidelines. But I think it's really important for us as a nation, to have a cadre of researchers and developers that explore the blue sky a little bit. It takes some time and just kind of look beyond the horizon. not all those ideas are going to pan out. Not all those ideas are going to come to a capability that we all enjoy, but some of them will. And the ones that do are the ones that you're really paying for, you're really investing in. And so, why should DARPA look at ISI? Why should sponsors look at an organization like USC ISI? I think the academic connection is important. I think the technical depth is absolutely essential. Right? Nothing starts without that. So that's like those are like table stakes. But beyond that, having an organization willing to take on really tough problems without being constrained on the risk side too much, I think is one element of innovation. So in the area of trusted microelectronics, trusted semiconductors, I actually look at that a little bit differently. I think of trusted systems that include hardware and software. And there's all sorts of ways to compromise a system by putting an exploit in the hardware or by putting an exploit in the software or some combination. But the ability of building secure systems, in my view, is the problem of the day, both for the DoD, both for our national security needs, but also for our commercial needs. Right? We all have an iPhone or two, or an Android or two, or half a dozen laptops floating around the house. I've got a mesh network at home with 50 or 60 devices hanging off it. You have no idea at any given point in time how secure that enclave is. You absolutely have no idea. There are no real-time indicators to tell you if you're being attacked or not. Industry has the same issue. Right? You do a transaction at your local ATM, or go into a Starbucks and buy a coffee using a touchpad. Starbucks and that bank are both at risk. So the problem that we have is, how do you build a secure environment that includes both hardware and software? And this problem is becoming much more complex as we've emerged into this IoT world, where everything is connected now. I drive into my garage, and all of a sudden my car is connected to my Alexa at home, and the lights go on, and this and that, and the Nest system is pre-positioning my heating system. And so this is a world that we're in. And having the confidence that you've solved the security issue by securing the chip supply, I think, is one part of the problem, but it's not the only part. And I think the challenge, the next, if you talk about moonshots, the moonshot here is to build a practice, the tradecraft, the understanding, the engineering discipline, the tools to really build secure systems from the ground up. And there are competing approaches to that today. And I think DARPA has done a remarkable job at starting that conversation. Everything from chiplet designs to secure CAD, secure computer automated design, to secured shared libraries. There's a whole range of projects that DARPA has started. But these are yet to be integrated across the industry into a practice, into a set of tools and tradecraft that are used in a very unified way. And so I'd say we're probably in the early innings of a secure systems industry that really is needed. If you think about the growth of complexity of the chips that we use and everything that they enable, the complexity of the networks that we operate in, that we use every day. I'm flying to Boston later today. There are half a dozen networks that I'm interacting with to make sure that flight transactions are right and travel's right and this and that. I don't even think about it, but it's all happening in the background. And yet any one of those, if it fails, it causes me a disruption, right? It causes revenue to change in some company. So that environment is emerging at remarkable pace. And in my view, the next sort of big moonshot here is understanding the tools, the tradecraft, the techniques and having a workforce that can actually implement secure systems end to end. Part of that might mean that you need manufacturing on US soil. Part of that might mean, okay, I'm actually confident that I can use packaging from some third-party country, a third-party partner elsewhere, but I'm able to track some security fingerprint or profile that gives me confidence that I understand that. And then, of course, another piece is the cyber attack surface and the cyber environment that you operate in, because we're all part of that. So I think it's a much bigger conversation than just secure chips. And I think the trusted foundry model was an entry into that, but not the complete solution for that. It was the right thing to do at the time, and I think a lot of thinking has kind of evolved to say, you know what, there's probably another way to look at this for DoD purposes and also for commercial purposes. The government works in interesting ways. They're remarkably dedicated people, and there are teams that actually do work, and they come together and they try to look forward in terms of, okay, what are the next big challenges for our nation, and how do we address those challenges? How do we encourage innovation in certain areas? How do we launch new moonshots? The last several administrations have done all of that, and I'm sure that the current one's doing that, and the next ones will. But against all of this, against this remarkable body of work, you think about, okay, I was part of the Defense Department, and our budget was, today it's on order $800 billion a year. The unclassified budget is, what, $850 a year? That's a pretty sizable budget. And against that, there's always a group of people, and you see them, I interact with them, it's a fun environment to be in, that are thinking beyond the horizon. Like, what's the next concept that we should take a look at? What are the next set of ideas that we should pursue? And a lot of those folks end up submitting proposals to DARPA. Some of them become DARPA program managers. Some of them are in other spots in government. But those are the ideas that we really were looking at. If I look back at the programs that really were impactful over the past several decades at DARPA, they kind of fit into several epics that parallel epics of government investment, DoD investment, that are called the offsets. The first offset was a nuclear triad. It was really looking at how we would counter Soviet aggression, in particular the ICBM threat in the early 60s. And DARPA had programs in that area. In fact, the first ARPA order was for the Saturn V booster. It was a 4 or 5 page contract to build the booster that gave President Kennedy the confidence to announce that we were going to go to the moon. Simple thing, but remarkable impact. And so that first offset carried on through the mid-70s. The second offset, Secretary Perry at the time, encouraged the department to make investments in precision strike, GPS, and command and control. And those 3 areas included a host of technologies that DARPA led. In fact, that's kind of when the epic of stealth started at DARPA, and other technologies started there as well. But they were tied to a view that Secretary Perry had and others had in terms of what we needed as a nation going forward. And of course that carried us well. This third offset, which is kind of when I was there, both as an office director and later as assistant secretary, was looking at the early inception and use of AI. This was something that had just starting to emerge from academia. And the question was, how could we use it? Not as a technology, but as a capability. What impact would it have? What problems could I solve using those techniques that I couldn't solve classically. And I had my list of priorities. Other folks that followed me have theirs, but they resonated on some similar topics. AI was one of those. Advanced microelectronics was one because it's kind of the underpinning, and other technologies. But we were kind of looking forward. What are the emerging technologies that are starting to bubble up, and how could we leverage those? And that kind of formed a lot of our thinking at DARPA and elsewhere. It's absolutely essential that we continue and we grow technology understanding amongst our youth and students that are matriculating through their careers. Whether they end up in a high-tech industry or not, it's important for people to understand the impact of technology that people use. Again, I'll reference the point earlier on, when I drive home, all sorts of things are happening in the background. I kind of know what they are because I set them up, but I don't know what everything is. I have no idea what's being attacked in my home from a cyber perspective. I'm willing to tolerate that risk, as we all are, because we don't understand how to measure it. But I think it's critically important as we look forward as a country that building technology understanding among students, even at an early age, is important. And building that awareness, I think, is critically important. Looking forward, I think security has got to be on that list. I think building technology awareness amongst the workforce has to be on that list. And having a channel of innovation with minimal risk, giving thinkers an avenue to try new things, critically important. Right. So I'll give you an example that I saw. I'm not going to name industries, but earlier in my career, we were doing facial recognition. And I'll just say the company that I was with decided not to pursue that as a product. And it made absolute sense. It made absolute sense because the algorithms weren't good enough. The algorithms were biased. And they were shown to be biased. Not intentionally, but they were. And so, again, understanding bias, understanding social impact of many of these technologies that, again, touch us day in, day out, critically important. Having ethicists on development teams, I saw that in industry. I think that's critically important. Making sure that the technology that we're developing, certainly in the commercial sector and in the DoD and for national security, is built in a way that it doesn't bias. That the bias is understood, that it's available to all to use. And that's, I wouldn't say that was a primary design principle as this whole thing started. It needs to be. It really needs to be. Oh, it's a challenge. There's no question that, this is not a cakewalk by any means. My experience is that certainly in industry and in government, people are attracted to the problem, right? It's if I wanted to get a first-rate team, I had to present a really tough problem and show that if you could solve this, you'd have a big impact. Seldom was compensation the first question. The first question, generally it comes into play, but generally the questions that I got from people that I was interviewing to join us, first question was, what am I going to work on, and what impact is that likely to have? And I think you could translate that into ISI coordinates. Building a clear story on what's the next challenge that ISI should take on. I'm working that with Steve and with Craig. And I think secure systems is one of those challenges. It's a messy problem. It's got multiple disciplines. It's not structured. It's remarkably complex. The ground rules aren't set. There are lots of opinions in the room. Not all are informed, right? So it's like the perfect storm for ISI to say, you know what, we're gonna peel this apart. We'll find the little niche that has a problem that we can understand, define, and quantify in some sense. And we've got a research team that can land and expand, that can solve that problem, then solve the next one and the next one, and start building an environment for a secure system end to end, to include trusted electronics, to include secure cyber, to include secure supply chains, to include all of that in some measure. Right now, those are parallel threads in a stream. They're all important, but it's not clear how they integrate yet. ISI is a remarkable organization. I mean, I've known it for quite some time. Very unique. You know, the combination of really remarkable people, technical depth, and the ability to try some new things has paid off. And I'm sure it's going to pay off for many decades.